All right, let's take a look at the Unit 4 practice assessment. The first question says match each element, nitrogen, carbon, oxygen, and hydrogen, with its correct number of covalent bonds that it would like to form. Well, there's something called the Honk 1, 2, 3, 4 rule, which says that hydrogens form one bond, oxygens form two bonds, nitrogens form three bonds, and oxygens form, carbons form four bonds. There we go. So we matched that. For number 2, we're supposed to match molecules with their potential isomer. It's kind of useful to just write out the formulas for each by counting up how many of each atom there are, because then we can really figure out, like, is it an isomer? Does it have the same formula? So let's see, this one is C2H6O. This one is C3H8O. And we've got C3H6O. And we've got C2H6O. Okay, let's get a different color here. So C6H8O, there's only one other one. Oops, C6. This is supposed to be C3. Oops. There's only one other one that has 3 carbons, 8 hydrogens, and 1 oxygen. And so you can see that these two are isomers. You can see that the OH group has moved from being on an end carbon to the middle carbon. So that makes sense. And then C2H6O, the second one and this last one, it's the same sort of a deal where we've got the OH on one of the carbons. I guess they're both end carbons, depending on how you look at it. And then here we sandwiched the oxygen between 2 carbons. So those are definitely isomers. And last but not least, C3H6O. These two should be isomers. We've got the double bond to the O between 2 carbons, and then we've got the double bond to the O after the 2 carbons, so on the end. So again, an isomer is the same formula, but a different arrangement, a different order of the atoms in their bonding patterns. So they have completely different properties. If a molecule is rotated 180 degrees, is it now an isomer? Let's take a look at Odyssey for this. So here's a molecule, and if I rotate it 180 degrees, is it now a different molecule? No, it's just rotated. So you could draw this in any rotation. You could rotate it 90 degrees or you know, over different axes. It's still the same molecule no matter how you rotate it. So no, it will be the exact same molecule, just rotated. The Honk 1, 2, 3, 4 says that carbon can't have 5 bonds. Why? Well, if carbon had 5 bonds, it's violating the octet rule, because each bonded pair is 2 electrons here. So 2, 2, 2, 2, 2, that adds up to 10, not 8. So each bond is a pair of electrons, and carbon wants to have the great 8, not the great 10. So 4 bonds would make 8 total valence electrons. So the second one is the only one that makes sense. Which of the following is the correct Lewis dot symbol for arsenic? Arsenic is in group 5A. That means it gets 5 dots. And remember, picture that there are 4 boxes, one on the top, one on the bottom, one on the right, one on the left, and draw your dots in a clockwise direction. 1, 2, 3, 4, 5, spreading out your electrons as much as possible. Okay, only we don't keep the boxes. So this would be the Lewis dot symbol for arsenic, which matches the top choice here. In a Lewis dot diagram, the most stable arrangement of electrons is when what? Well, the most stable is when it has the grade 8. So it would be when you've got 4 pairs of electrons surrounding the atom. Match each Lewis dot diagram with how many covalent bonds it would like to form. So remember, we look for lonely electrons. Those are the ones that want to form a bond. So this first one has 4 lonely electrons, so it will want to form 4 bonds. The second one here only has 1 lonely electron, so it will want to form 1 bond. This one doesn't have any lonely electrons, so it's not interested in forming a bond. And this last one, good, it makes sense. There's 2 lonely electrons, so it wants to form 2 bonds. Which of the following elements would make 2 covalent bonds? Now, a covalent bond is between 2 or more nonmetals. So if something is a metal, we have to eliminate it because it would not form a covalent bond. So the first element is calcium. Calcium is to the left of the zigzag, which means it's a metal. So it cannot be this one. Let's check out oxygen. Oxygen is in group 6A. So when you draw the 6 dots, ooh, it does have 2 lonely electrons. So yes, this is the answer. Oxygen would want to make 2 covalent bonds. Select the correct Lewis structure for the formula C2H2O. Well, I like to draw my own first. And there's more than one right answer for this because it just says select a correct structure. But let's give it a shot. I'm going to point lonely electrons toward each other. Carbon is in group 4A, so it gets 4 dots. Oxygen is in group 6A, so it gets 6 dots. I want to connect everything one time before I start connecting other things. So now I've got a place for a hydrogen up here. I've got a place for a hydrogen right here. And then this is going to be a little messy. There's a double bond between the carbons and a double bond between the carbon and the oxygen. So if I redraw this nice and neat, which this problem doesn't even do, I would see that there are 2 double bonds, one between the carbons, one between the oxygens, which is shown in this last choice. Now again, I could have chosen a different structure, which wasn't one of the options, but I do want to show an isomer of this just for fun. Connect everything once, and then what if I had put a triple bond between the 2 carbons, and then I put the hydrogens on the oxygen and the carbon? That would also be a correct structure, just as an FYI. Put the following steps in order for how to draw a Lewis structure. Well, step 1 is always put atoms that are at the start of the formula in the middle, unless it's hydrogen. So if you've got a molecule like C2H5OH, for example, you want to put the carbons in the middle. And then step 2 is to start drawing their Lewis dot diagrams and figuring out how many bonds each can form. And then step 3 is start bonding atoms together like a puzzle and make sure you follow the octet rule. You'll know you're done when there's no more lonely electrons to pair up. Draw the Lewis structure for C2Cl2. Okay, let's go to the periodic table. Carbon's in group 4A, so it's going to get 4 dots. Chlorine is in group 7A, so it's going to get 7 dots. Molecules like to be symmetrical, so I'm going to draw my carbons in the middle, and then I'm going to draw my chlorines, which each have 7 dots on the 2 sides, showing the lonely electrons pointing toward the carbons. And I want to connect everything once first. And I still have 2 lonely sets of electrons, so I want to connect those. And I'm redrawing it nice and neat so my triple bond is very clear and still adding my lone pairs. There we go. 2 linear shapes. Which of the following is true about CO2? Draw the structure out to help you. Carbon's in group 4A. Oxygen is in group 6A. So it gets 6 dots. Connect everything once. Then go crazy with your double bonds here with the lonely electrons. So if I'm redrawing this nice and neat, here is carbon dioxide. Option 1, the structure has 4 bonded pairs of electrons and 2 lone pairs. Well, it's true that it has 4 bonded pairs, 1, 2, 3, 4. So again, the highlights equal bonded pairs. But let's count up the lone pairs. 1, 2, 3, 4. So there are 4 lone pairs. Oops, I should just put the key, lone pairs. So number 1's not correct because it says there's only 2 lone pairs. Option B, the structure has 1 triple bond. No, that's not true. The structure has 1 double bond. No, that's not true. It has 2 double bonds. Last choice, it better be this. It has 4 bonded pairs, 4 lone pairs, and 2 double bonds. Yes. Which of the following is a correct summary of Vesper theory? Electrons, whether in a bonded pair or lone pair, have positive charges. No, electrons have negative charges. Electrons, whether in a bonded pair or lone pair, have negative charges which attract one another. No, they repel. Electrons, whether in a bonded pair or lone pair, have positive charges. No. Electrons, whether in a bonded pair or a lone pair, have negative charges which repel repel one another and dictate the molecule shape. Yes. All right, and then let's sketch these. We've already seen CO2 recently, so we got a sketch for that one. SiH2O. Si has 1, 2, 3, 4 because it's in group 4A. Oxygen has 6 because it's in group 6A. So I'm going to connect them once. And then there's 2 hydrogens to put into place, which means that there will be a double bond between the Si and the O when I redraw this neatly. And then let's draw CF4 over here. Carbon has 4. Each fluorine has 7. So there'll be 4 fluorines, 1 on each side of the carbon. And then PF3, P has 5 electrons because it's in group 5A. And then it's got 3 fluorines, each which can form 1 bond. So let's get these guys into place. And H2S, sort of like H2O, S has 6 lonely electrons. And yay. Now we can decide which shape goes with which. So CO2 has a linear shape because it has no lone pairs pushing down those 2 things. So CO2 goes with linear. SiH2O has 3 things surrounding it and no lone pairs, so that's trigonal planar. CF4, kind of the giveaway one, it has 4 things attached. That's tetrahedral. And then let's do PF3 has a lone pair and 3 things attached. So the lone pair pushes down those 3 fluorines into a pyramidal shape. And then there's only one left, H2S. Because of those 2 lone pairs, even if I had drawn it like this, it's still a bent shape in 3 dimensions. What shapes are present in the molecule pictured? Well, I can see around this blue atom that there are 3 things attached and they're not in a planar shape. So this one must be trigonal pyramidal. And then this one has 1, 2, 3, 4 things attached to the central atom. So this is tetrahedral. So tetrahedral and trigonal pyramidal, it's the top choice. What shape would the molecule pictured have in 3 dimensions? The answer is bent. A lot of people choose linear, but remember the toothpicks. If these are getting as far away as possible in 3 dimensions, it would be, they'd be further apart than if they're linear. So here would be a linear drawing. This is a lone pair. This is a lone pair. This is the eye. This is the eye. Okay. So if it was just like this, these would be 90 degrees and this would lay flat. Okay. But it's not this way because in reality, these can like kind of come up out of the screen at you. Okay. These 2 iodines, and then these lone pairs can be like going away into the screen. And so then they're each 109.5. And so that's why it's a bent shape and not linear. All right, hopefully that helps you out.